In this class, we're going to take a look at some examples of using the chain rule. So in the previous class, I explained that the chain rule is technically for finding the derivative of composite functions, but the functions are not always obviously composite functions. They're not going to tell you that it's a composite function. And part of the challenge with the chain rule is knowing how the technique works, but more importantly, I think recognizing when you even need to use the technique of the chain rule. So for example, if you look at these questions I've got here, they all look very, very different. Now in the previous class, we looked at two examples that were kind of this format here, where you've got a bracket with a power, and that is probably the most common scenario, at least initially, that you'll see chain rule questions presented in that format. But you'll see other formats as well, and none of these really look to be very similar. So it's kind of a bit of a surprise initially that you can use a chain rule for all of these. But that is the beauty of the chain rule. That's why it adds so much more versatility to the types of functions that you can differentiate. So I mentioned in the previous class that there's a couple of different ways to think about the actual rule, the way the rule's written. One is in sort of Y terms, the other one is in sort of F and G terms. They both say the same thing. We can also then think about particular formats of the chain rule, in particular these guys, which I refer to as a sort of general sort of power rule, which is basically when you've got a bracket with a power. This one's also going to use the product rule, so chain rule and product rule mixed into one question. And we also said that you can use the chain rule formally by writing out like a whole bunch of steps, and sometimes you might have to do that. That might be the way that your teacher, your class wants you to do it. But you can also use a more intuitive method to use the chain rule, which is effectively just, in a lot of scenarios, using the power rule twice. So we'll maybe work a couple of these both ways, but the point is really in this class to just start to recognize all these different formats in which you have to use the chain rule. Okay, so let's start with this guy over here. Now, this one is in the format to use that sort of general power rule, and that general power rule basically says that you can go straight to your derivative without really too much sort of faffing around, and you can just go straight to it by saying that you multiply the power in front, effectively doing the power rule on the whole bracket. So multiply the power in front. There happens to be a 2 in front here as well, so the 3 will come down and multiply in with the 2 to make a 6. Leave the bracket alone, reduce the power by 1. So notice that effectively what I've done there is the power rule on the bracket. Multiply by the power, reduce the power by 1. The chain rule then says multiply that by the derivative of the inside of the bracket, which in this case is -5. I got that using the power rule. The power rule on 4 minus 5x would give me a derivative of -5. Take one more line just to tidy these up by multiplying these numbers together. No differentiation at that point, just multiplying the numbers. So that gives us -30 bracket 4 minus 5x all squared. Okay, so that would be using that kind of general power rule, and which is kind of the less formal way to do things. If you need to do this a more formal way, you would define the inside of this bracket as being like your internal function as maybe u. U tends to be the common letter we use for that. So we'd say let u be 4 minus 5x. That then tells us that du dx, the derivative of u with respect to x, the derivative of this here, is -5, okay? And because we've defined u to be this here, this is now 2u cubed. So the function y can now be written as 2u cubed. If we use the power rule on that to get dy du, we get 6u squared. And then the overall kind of format of dy dx, which is what we're trying to find, remember, we're trying to find the derivative of y with respect to x, can be written as dy du times du dx. Okay, now dy du is this guy here, so that's 6u squared. Dy dx is this guy here, which is -5. Multiplying those together and we get -30. I think you probably see where this is going, u squared. And then we can back substitute our u to get -30, to put the u in a bracket, which is because it's got two terms, so 4 minus 5x squared. So basically all of that work in there which is absolutely fine. I mean, it's great. It's exactly what the chain rule says. Gives us that result. Using the more general power rule, the shorthand version, if you like, gives us exactly the same result. There might be scenarios where you're asked to do it like this. There might be scenarios where it's maybe even better to do it like this, but this is equally effective for that particular format, not for every format. That's not going to work, for example, really for this. Well, it is kind of going to work for this guy, but it's not really the format it's intended for. Like, this power rule works best when you've got like bracket with a power, basically. Okay, right, let's have a go at this guy here. I think I'm just going to have to move this down. I don't think I'm going to have enough space to do this one all in that one little piece. So let's go, I think that was 1 minus x, and I think it was a y function. Okay, right, so this guy here, this is in the format to use the chain rule because it's a bracket with a power, basically, which is a composite function. But we've also got the added difficulty here that we've got this x squared term in front. So we're actually going to have to use the product rule here as well. Now, this is not uncommon to have to use like multiple rules. So just cast your mind back to the product rule, or if you're not familiar with the product rule, just follow along here and then maybe check out the product rule in another class. Okay, so we covered the product rule in a previous class in this series. The product rule tells us to take the derivative of the first term, which is 2x, or there's different ways to think of the product rule. This is the way that I personally prefer to think of it. The derivative of the first term, leave the second term alone, or the second function alone. This is function 1 and function 2. And then take the derivative of the second function, which is this guy, the one we're going to have to use the chain rule on, multiply to the first function. So the derivative of that second function is when we're going to use the chain rule. So the 3 comes down in front. The bracket stays the same. We take 1 off the power, and then we multiply by the derivative of the inside of the bracket, which is 3. And we need to multiply all of that. That's all there, just the derivative of that times to this guy here. So I'm going to put all of that in a bracket and then put an x squared on the end there. So it's quite messy, this one, in terms of algebra, but this is the kind of level you need to kind of aspire to, because you will see a lot of questions like this. So just trying to tidy this up now. We'll leave the first term alone for the time being, and we'll work more on the second term. So notice that with the second term, the 3 and the 3 can combine to give you a 9. The x squared could come in front to make it a plus 9x squared, 3x minus 9 to the power of 2. That's okay probably to leave it at that point. You could pull out common factors. In fact, let's maybe take it one line further. There's a common factor here of x, and there's a common factor of 3x minus 9 squared. So we could go x bracket 3x minus 9 squared. That would be our highest common factor. And then maybe using a square bracket, so we would need to multiply this guy here by 2 and by 3x minus 9, because that bracket times 3x minus 9 gives you that bracket cubed. Okay, and then we would need to multiply this here to get this term, which would be plus 9x. Okay, and I suppose we could actually go further with this one. The way the algebra is working out means that the inside of this bracket will tidy up. So if you multiplied out this bracket here, you would get a 6x. Yeah, but you can add that to the 9x to give you a 15x, and then 2 times minus 9 gives you minus 18. And I think that's probably as far as we would take that one. That's it in this kind of form. You might want to spin it around to put the squared bracket second. It's really up to you, but that would be it pretty much done at that point. Okay, so both the chain rule there and using the product rule. This guy here, well, the first thing is that it's not really in a format that matches up with anything else we've seen. But remember that from your indices or your exponent rules, that you can rewrite a square root as a 1/2 power. And you'll see this quite a lot actually, where you've got some kind of root, you're going to turn it into some kind of power, which then means it is in the format to use some of your rules. In this case, a bracket with a power, so therefore we can use the chain rule, hence why we're using this example. So we're just going to go through this one in the more intuitive way. So we're going to go straight to our derivative by using this sort of general power rule, which I used up here. And the general power rule says, multiply by your power, reduce the power by 1, just like you're using the power rule on the whole bracket, then multiply that by the derivative of the inside of the bracket. The derivative of the inside there is minus 1, using the power rule. The minus 1 can come in front to combine with the 1/2 to give you minus 1/2, bracket 1 minus x to the minus 1/2 power. You might want to rewrite the bracket with a positive exponent, and you could even bring the 2 down to the bottom of a fraction, so it could wind up being minus 1 over 2 bracket 1 minus x to the 1/2 power. You could even rewrite now that 1/2 power with a square root if you wish, so it would be minus 1 over 2, oh, I should really make my fraction a bit bigger there, 2 square root 1 minus x. Okay, just to tidy it up as fully as we can. So slightly different case there, but you will see quite a lot of those, so pay attention to that type of format. Okay, let's look at this one, sine 5x. If you've already watched the class on differentiating trigonometric functions, you'll know that we can just go straight to the answer to this. It's very, very straightforward. And there is basically a formula, if you like, but technically this is the chain rule because you've got a function 5x inside the function sine, which means that it's a composite function. And if it's a composite function, then we have to use the chain rule. But if we think about it, the chain rule really just says take the derivative of your overall function, which is the whole thing. Well, the derivative of the whole thing is the sine function. The derivative of the sine function is the cos function. Okay, so sine turns into positive cos. Then the chain rule says basically now multiply that by the derivative of your internal function in the same way that the internal function here had a derivative of minus 1, the internal function here had a derivative of minus 5, etc. So the derivative of the internal function 5x is just 5, so we're multiplying that by 5, so we just get 5 cos 5x. So it is important to know that that is the chain rule, but really you just kind of learn to pull the 5 in front. But you do see variations on that, and we looked at that in the class where we did trigonometric derivatives, where sometimes the internal function will be more complex, and rather than just saying, okay, I'm going to pull that number 5 in front, you've got to actually think more about the fact that this 5 is actually the derivative of the inside internal function. But that's more important now because we're thinking of that in terms of the chain rule. Okay, this one's a little bit more explicitly the chain rule, but again, in the original format, kind of like this one, it's not entirely clear that we do need the chain rule because cos cubed x, is that a trigonometric derivative or what's going on there? Well, just remember that what cos cubed x means, it really means cos x all cubed. That's just notation. We pull the 3 to the kind of middle part just to avoid the confusion of writing cos x cubed, which would actually mean the cosine of x cubed, which is not what we want. So that's just a notational thing that you've probably seen before. If not, we just pull the 3 there to avoid that confusion, because that and this is not the same thing. This is what we want. So if we take its literal definition, which is like cos x all cubed, then we can write it in a bracket, because that's what that really means. Now that is in the format to use the chain rule. So applying our kind of general power form of the chain rule would say multiply the power in front. Okay, leave the bracket alone to give you a cos x, take 1 off the power, so it goes down to a squared, and then the derivative of cos x is negative sine x. So we're multiplying this by negative sine x. So these guys always come out a little weird in that you end up with like a second trig function. And then just tidying this up by multiplying the 3 and the minus sine x, we would get minus 3 sine x cos. You could remove the bracket and make it cos squared x if you like at that point. So those guys are fairly common actually. You'll see quite a lot of those. I always encourage students to make this line of working just to explicitly put it in the format of a bracket with a power. It both helps remind them that this is the chain rule, and it avoids the scenario of trying to differentiate it in this format, which can sometimes cause a little bit of confusion as well. So good practice just to write it in that form and then take it forward using the chain rule. You could go ahead and solve this derivative using this method as well. You would let your u be the internal function, which is cos x. But I think we're starting to see now that although this method is technically correct and it's fine and sometimes you need to use it, it's a lot longer. There's a lot more work involved. If I take this over here, I can barely fit it on my whiteboard, right? It's going to spill down there somewhere. So if you get comfortable with this method, as long as you remember that this is a kind of shorthand way of basically doing this, and if you do these side by side, you can see that the working that you're doing for this is exactly mirrored by this longer working. This is really almost more just following along with particular notation. It's more the notation here that's really taken up all the space and the time rather than the mechanics of taking the actual derivative. So I hope that that helps, seeing these different formats. They can vary quite wildly in terms of the format in which you can apply the chain rule. Like all the derivative rules, and particularly the chain rule, the importance for you is to spend time working different examples, seeing different examples so that you know what rule to apply. Because by now you've probably learned the power rule, the product rule, the quotient rule. Now you've got the chain rule and you've got the trig function. So you've learned probably at least 5 techniques. And it's not always easy to know which technique is applicable to which function types. And as we saw in this example here, sometimes they're even mixed. So I would encourage you to work many examples, as many as you possibly can, before you go crazy with seeing too many examples, just to get comfortable with these different formats and which rule you need to use. So practice is really the key with differentiation. So I hope that makes sense, and when you're ready, go ahead and check out some practice questions.